So the multiplication rule is, again, just a way to generalize what we looked at in the previous section. So to generalize that, we can say that because the probability of A conditioned on B is equal to the definition of conditional probability, the probability of A intersected with B divided by the probability of B, then the probability of A intersected with B is equal to the probability of B multiplied by the probability of A conditioned on B. That's exactly what we looked at in the previous slide. Now, we can also say that the probability of A intersected with B is equal to the probability of A multiplied by the probability of B conditioned on A. Now, you may be looking at that a little bit strangely at this point, but remember, we said that in intersections, the order does not matter. And so in this case, those two equations, right, of probability of B conditioned on A and A conditioned on B, both had in the numerator on the normal conditional probability formula, both had the probability of A intersected with B. What varied was the order of the terms in the conditional expression and the denominator. So we've really just replaced those two in this specific scenario. So the question that we might ask based on that is, this works great for two stages, right? We had a probability of a plane in the air and then of a radar triggering that. But what happens if we have an event with a third stage? So if we draw out a tree diagram for that, and in this case, we'll actually assign the labels as we go. Let's say that we have three events, an A, a B, and a C. Well, the first thing that we have is a probability of A and a probability of A complement. Then we'll have a probability of B given that A has occurred. And then we'll have a probability eventually of C given that both A and B have occurred. Now, how did I get there? Well, remember we said this is just A. And it would follow, based on our previous example, that this is A intersected with B. And then this would be A intersected with B intersected with C. And we can continue to layer all of these out as we go. So let's look at a specific example here. We can derive this out in a general form, but let's say that we're looking at the probability of A complement intersected with B intersected with C complement. So if we trace that out from a path perspective, we're going to go down our lower branch, and then we're going to take the B, and then we're going to go down C complement. So we're kind of following that general order down our tree to land at this node here, this leaf. And so if we wanted to turn this into a mathematical expression, though, what we would need to do is first say, what is the probability here? And the first thing we can do is group these intersections. So we can say that this is the probability of A complement intersected with B, and wrap that in parentheses, and then intersect that with C complement. And that'll make things a little bit easier here in a second. And the reason for that being that we can plug this into our conditional probability equation. What we can do based on our previous slide, we can say that this is equal to the probability of A complement intersected with B multiplied by the probability of C complement conditioned on A complement intersected with B. And again, that just follows from our conditional probability equation that we flipped back into the general multiplication rule. Now, from this, we can go a step further, and we can say that that is then equal to the probability of A complement multiplied by the probability of B given A complement multiplied by the probability of C complement given A complement intersected with B. Now, from here, what we've established is that we're looking exactly now at the layers of our tree, right? We've said this is the probability of A complement. Well, this one here would be the probability of B given A complement. And then this last leg here is the probability of C complement given A complement and B have both occurred. So we've actually written out now the probability of all three of these occurring is equal to the product of the respective branches, which follows from our previous example. This is just the mathematical proof behind it. So if we wanted to generalize this, we can actually go so far as to say that the probability of any series of A sub i's. So we'll say this is the probability of A sub 1 intersected with A sub 2 intersected with A sub 3 intersected all the way out to A sub n. Well, in this case, we can say that that probability is equal to the probability, and we'll pull out the A sub 1 just for simplicity, but then put that into a product, and a product specifically from I equals 2 to n. So the product, remember, is just the capital pi. That's I equals 2 all the way up to n of the probability of A sub I conditioned on A sub 1 intersected with all of the A's up to I minus 1. And if we close out that product, this isn't necessarily the prettiest formula to look at, but this is the generalized form that says multiply all of the branches as we progress through this tree in order to find the probability of arriving at this event. Now, let's take this and look at it in a different practical example to make sure that we fully understand the concept. So let's assume that we have a jar that has 8 red balls and 4 white balls. And if we draw 2 balls from this jar without replacement, so we're not putting the first one back in, what is the probability that both of the balls that we pick out are red? And then we'll assume that each ball is equally likely to be chosen. So in this case, we can say we have 2 events. We have an event D sub 1 that is that the first draw is red. And then we have D sub 2, which is that the second draw is red. So with those in mind, we can then start applying some mathematics to this. And what we're really looking at here is what is the probability of both D1 and D2 occurring. So this is going to be the probability of D sub 1 intersected with D sub 2. And in this case, we can look at the probabilities of each of these phases individually. The probability of D sub 1, the probability of drawing a red ball on the first draw, is just equal to the number of red balls, 8, over the number of total balls, which is 12. So 8 twelfths. Now, the second piece, the probability of doing a second draw, is a little bit interesting because we have to assume that we pulled a red ball the first time. So in this case, we can say we're really more interested in the probability of D2 given that D1 already occurred. What's the probability of drawing red, assuming we already drew a red ball the first time? And in this case, we can say that the conditional probability is actually equal to 7 out of 11, right? We've removed one red ball, so we're down to 7 red balls. And we removed a red ball, so we're down to 11 total balls. So the probability here is 7 out of 11. Now, it's convenient that we landed with these two equations here because, as you may recall, the probability of two intersected events is equal to the probability of either event. In this case, we'll say the probability of D1 multiplied by the conditional probability against that event. So this would be the probability of D2 given D1. And we have both of those factors. We have probability of D1 is equal to 8/12ths, and we have the probability of D2 conditioned on D1 is equal to 7/11ths. So we can say that the probability of drawing red on both the first and second draw is just equal to the product of these two probabilities we just calculated. So 8/12ths multiplied by 7/11ths is equal to 14 out of 33. So the total probability in this case of drawing 2 red balls is just equal to 14 out of 33, or a little bit less than 1/2.